Hello everyone, we are pleased to present our ICCV paper, 3DS 3D shape reconstruction with implicit algebraic surfaces. In this work, we propose a new primitive-based 3D shape representation for single-image 3D shape reconstruction, which is a challenging task. To achieve a detailed 3D shape, it is essential to select a good representation and a proper DNN-based method for learning this representation. Primitive-based 3D shape representations can model complex 3D shapes with a combination of basic geometric forms called primitives. While these representations have various advantages in computer graphics applications, previous methods are still limited by the simple topology of the primitives to obtain the detailed 3D shapes. We propose a specific 3D shape representation as a union of design constrained implicit algebraic surfaces. The implicit algebraic surfaces have high degrees of freedom, which enables them to form more geometrically complex shapes than simple primitives. Therefore, representing 3D shapes requires fewer primitives. We apply a set of constraints on the defined implicit algebraic primitives to better approximate the surface of a 3D shape. Easy visualization and rendering attributes for a 3D shape representation can be useful in many computer graphic and virtual reality applications. We use multivariate quartic polynomial functions as the primitives because they have the highest degree of freedom among all implicit algebraic primitives with the closed-form algebraic solutions, which provide sub-rendering. We need to ensure that the final reconstructed 3D shape has a closed surface, or equivalently, all primitives have closed surfaces. To achieve this goal, the summation of fourth-order elements must always be positive. Furthermore, we developed a scale constraint to ensure that the volume of each primitive is smaller than the target 3D shape. We designed this constraint by considering a learnable upper bound Q for each primitive P. Therefore, our primitives can be parameterized with a learnable symmetric matrix B and a learnable parameter R. We also encourage the primitives to cover different parts of a shape by transferring their centers to the desired location C. To reconstruct a 3D shape from a given input image, we employ a deep neural network to learn the matrix B and the parameters of R and C of the primitives. Then, we apply a min operator as a union on the learned primitives to reconstruct the final output. The implicit algebraic primitives, like other implicit functions, divide the space into positive and negative signs. Therefore, we define the sign loss to map the points inside and outside the shape to negative and positive values respectively. The sign loss also maps the points on the surface to 0. The sign loss enforces the network to reconstruct the desired surface and refuse to generate the redundant surfaces simultaneously. We also define the normal loss for the points on the surface to learn the second-order information. We train the network with a weighting average of the defined losses. We illustrate that the proposed constraint primitive is able to form more geometrical and topological complex shapes. This leads to obtaining a more efficient and proper representation for very complex 3D shapes. We also show that our network learns a semantic structure without any part-level supervision, such that one primitive usually covers the same part of reconstructed 3D shapes in the same class. Moreover, we show that our method can achieve better performance compared to state-of-the-art methods, and outperforms them with most of the metrics. More experiments and explanations are available in the paper. In conclusion, we propose a primitive-based 3D shape representation including constrained implicit algebraic surfaces and a learning framework to learn their parameters. We illustrate that our method can learn semantic meanings without part-level supervision. We qualitatively and quantitatively demonstrate that our method outperforms state-of-the-art methods. In the future, we will develop a sub-renderer by utilizing the solvability of the design primitives to reconstruct the 3D shape with self-supervised learning. Thank you very much for listening. Our code and the pre-trained models are available at GitHub.